Good afternoon. This is Josh Person. Thank you for attending this. It's 2 o'clock right now. Going to wait for a minute or two and then we're going to get started. So please be patient. All right, it's 2 minutes after 2. I'd like to start my presentation. I appreciate all the attendees who have logged on. Today, I'd like to talk about robotic vision. My presentation is Born to See, integrated machine vision used to guide robots in manufacturing. The born part, I don't mean to imply that our robots are organic or that any are organic. It's just a catchy title that they asked me to come up with. So my name is Josh Person. I'm a staff engineer here at FANUC America Incorporated in Rochester Hills, Michigan, right outside of Detroit, Michigan. I'd like to go over, primarily vision and talk about how vision and robots can interact and kind of what's going on, help you guys with your manufacturing needs. So my agenda, I'm not going to drag on and on here. We've got a nice, quick, tight presentation today. I'm going to start off with what is integrated robot vision? Integrated versus PC-based or smart cameras. So I'm going to kind of go over the difference between the integrated robot vision, a PC-based vision system, and smart cameras. Then I'm going to talk about mounting the cameras, either a robot-mounted camera, so you can mount a camera on a robot and move that camera around wherever the robot can move. Or you can have a fixed camera where you mount it permanently to a structure, and you can have multiple fixed cameras. You got multiple robot mounted cameras, and even some applications have a mixture of each. Then I'm going to talk about robot guidance, using the vision system to guide the robot. Basically, where is the part? Based on the vision system, you can move the robot as the part moves or changes its location. Versus inspection, where the vision system is just looking at the part, deciding if certain characteristics are good or bad, or error proofing if a previous operation happened or didn't happen. And sometimes you can mix the robot guidance along with the inspection or error proofing, to give you, a fully intelligent robot system. Then some applications require a 2D vision system and some require a 3D vision system. So I'm going to talk a little bit about the difference between those. The 2D vision system will give you X, Y, and rotation. It'll assume the part is sitting flat on a surface, and thanks to gravity, many parts sit flat either on a conveyor belt or a fixture or whatever your work surface is. So 3D isn't always necessary, but sometimes it is. Maybe your part is going to be stacked at different heights. Maybe they're going to be stacked on top of each other and have a tendency to lean. Maybe they're hanging from a chain and can swing a little bit or be out of control as far as its location. You can use vision system to find those parts in 3D. So many applications are 2D and many applications are 3D. Then I want to talk a little more specifically about inspection and error proofing. Oftentimes they're used interchangeably, but that's not really the case. A lot of times inspection is more of a complicated, checking for surface flaws, looking for cracks, dimensional tolerances, metrology, really looking at the fine detail of the part to make sure it's good or bad. Whereas error proofing might be considered generically as gross inspection. Did the previous operation happen? Is the part upside down or right side up? Is it the correct part? That kind of thing, where you're not looking at, is the thread pitch correct on your bolt? You're looking at to make sure the threads were actually cut in the bolt. So it's more of a presence absence versus, pitch and, checking the entire bolt completely. So I'll go over that kind of stuff. So bear with me. So why would you add vision to a robot work cell? Not every work cell needs vision. Some of them are perfectly happy doing the same thing over and over again. The robot's very good about going to exactly where it's told every time. The automotive body might come into the assembly line, get lifted up into place, exactly the right spot, and the robot can go and start doing its spot welding. If that auto body is in the same spot every time, maybe you don't need vision. Maybe you can just always go to the same 232 locations and do your spot weld. Everybody's happy, there's nothing going on. But as soon as something like that auto body is not positioned in place exactly every time, well, then the robot would struggle unless you added vision to figure out where that is and offset all of your points based on the location of that part. So machine vision is used in many areas of manufacturing, automotive, non-automotive, machine load or unload, but anywhere a robot is used, vision has the potential to improve it. Even the farming industry that uses robots, the vision can be used to find the chickens or something. So some oddball applications out there. A lot of times it's great for machine loading and unloading. Today I want to focus on machine vision for the robots. Machine vision can be used on many different assembly lines or applications. Maybe it's a high-speed vision system inspecting the labels on a bottle. As the labels go by as fast as the eye can see, the camera snaps a picture and makes sure that it's the right text, make sure it's in the right spot or right location. Well, that's not really a robotic application. The robots can't keep up with those high-speed lines. So I want to focus on machine vision for robotics, not just general manufacturing. When you add a vision system to a robot system, it gives you some pretty inherent benefits. It might reduce fixturing cost. So to get the part in the exact same position every time might take a complicated fixture with some moving parts, special sizes, something that somebody might have to design specifically, and it might be complex. If you have a vision system, the part entering the work cell does not have to be in the same location every time. The camera, either 2D or 3D, can locate it and drive the robot over to pick it up. So if your fixturing is less complicated, it makes it for easier changeover. Many manufacturing cells don't run the same part 24/7. They either run a family of parts or completely unrelated parts. Well, a vision system can help you find, maybe one day it's finding the first part, and then, the next shift is finding the second, and the third shift is finding a third. And there's hundreds of parts some manufacturing areas run. And the vision system can identify those and drive the robot to pick them if that's what your application is. You can also future-proof your manufacturing application with vision, because if you don't need to have specific fixtures, when you come up with a new part that might be slightly bigger or slightly smaller, you can use the same vision system to locate that one as it sits flat on its work surface, as opposed to designing another fixture to hold it perfectly in the right spot every time for the, for the blind robot. So vision can help add the flexibility. Also, it can help the robot make better decisions. You're adding intelligence to the robot. Instead of the robot just going to a program point, picking a part, moving to a program point to drop off the part, maybe it can figure out where is that pick point using vision, or where's that drop point. So you can figure that stuff out. It can see if the part's upside down or right side up. It can even do some inspection or error proofing. If it finds a part and knows that it is bad for whatever reason, maybe instead of loading it into the machine, it can load it into the rework bin or the scrap bin. So you can have an intelligent robot figure things out. If the wrong part came in, instead of just picking up and trying to jam it into the machine, it might know that it's the wrong part and alert the operator that there is an issue, or better yet, figure it out and do an automatic changeover. But that's all kind of part of the overall system, and vision can help you realize that goal, whether you're using it for robot guidance or error proofing and inspection. So I like integrated robot vision myself. That's my day-to-day job is to support the integrated robot vision product at my company here, FANUC America. So integrated robot vision is simply the vision system is part of the robot. The vision system was designed and developed by the robot manufacturer. So all robots, no matter the manufacturer, they can benefit from any sorts of vision system. There is many off-the-shelf third-party vision systems that are fully featured, very good, lots of good specialty. One might specialize in one thing, another might specialize in another thing. From a robot's point of view, those third-party vision systems are just remote sensors that give inputs to the robot to help it make decisions. And every robot manufacturer can connect to peripheral equipment, different sensors, or the machine vision system connects to the PLC, and the PLC can make the decisions for the robot. So machine vision on robots, that comes in all shapes and sizes. But what I want to talk about is the integrated robot vision, where the vision system is directly integrated by the robot manufacturer into the robot controller. And what that gives you is a seamless interaction between the robot and the camera. Since the vision system is part of the robot, there isn't even a concept of getting the vision system to talk to the robot, or getting the two on the same page, or getting them set up or calibrated. That doesn't exist because they are the same thing. So you would plug the camera into the main CPU of the robot, and bam, you've got your vision system. One major advantage of that is your single point of support between the robot and the vision system. In any manufacturing system, especially one with the robot, if the robot stops moving, then all of a sudden, production's down and it's the robot's fault. But why didn't that robot stop moving? Well, maybe the vision system didn't find the part, or maybe the robot moved to the part incorrectly. Well, is that the vision system that messed up, or the robot that messed up? Who do you call first? Do you call the robot support hotline and tell them, my robot's no longer picking up the part, and they're going to dig into it and find out that probably the vision system messed up. So then you're going to call the vision system supplier, and they're going to dig into it and find out, no, it was the robot that messed up. So now you've got two separate people blaming each other, and where do you go from there? If you have the single point of support between the vision system and the robot, there is nobody to blame. If the robot's not picking up the part because of the vision system, it's the robot manufacturer's problem. If the robot's not picking up the part because of the robot system, it's also the robot manufacturer's problem. So not having somebody else to blame is really, kind of a blessing in my industry. It might not sound like it, but it really is. And another thing that is nice is the robot manufacturer has control over the reliability of the vision system if they own it, if they develop it. Otherwise, the robot manufacturer or the robot system is relying on the reliability of a third-party vision system that, they might be a very strong and reputable company, or they might be fly-by-night. There's all sorts of them out there, everywhere from A to Z. So the reliability of the integrated vision system is on par with the reliability of the robot because it is the robot. So I'm talking about integrated vision, but there is PC-based vision and there's smart cameras, and all those solutions have their place. One of them isn't the best for everything. Each one has its advantages and disadvantages, and go over them a little bit. With the integrated vision, since the vision is part of the robot, you can plug the camera directly into the controller, and if it's a robot-mounted application, which some are not, you can use the camera cable that is run up internally on the robot arm by the robot factory that is all engineered and designed to go up that arm perfectly to have a higher chance of reliability. You don't have to run the cable up the outside of the robot arm and try to engineer it yourself. Anybody who has experience with robots knows that robot cabling, especially out on the end of arm tooling, is a very important piece of the puzzle that you have to get right, or else you're going to have downtime. So the pre-run by the factory camera cable is a big advantage. But if you have a PC-based vision system, the camera is plugged into the PC through a frame grabber, and the PC usually communicates the vision result to the robot or the PLC, and the robot can respond to whatever information the PC or the PLC gives it. A PC can be as powerful as you can spec out. It can do lots of number crunching, quite a bit faster than the main CPU of a robot. And you could add 100 cameras all doing special things to a PC, just keep improving the PC's hardware. So there is lots of opportunities for a PC to shine if you have a complex problem that you need to solve. The challenge is with the PC is then you have the reliability of the PC to worry about. Then you have the reliability of the third-party frame grabbers, the cameras, the I/O card, Windows. You've got different things to worry about when you're setting up this PC-based vision system. Even though it's an industrial PC, there's a good chance it's running Windows under the hood. And I don't know if I'd want to have Windows support my production system. Very good operating system, but it's got a lot going on, a lot on its plate. In my robot company, we had PC-based vision system, in the early 2000s, and we got off it and went to an integrated vision system. And it was awful nice when the support calls came in that I wasn't getting calls about Windows crashing, because not being a PC programmer, sometimes I really didn't know why their PC crashed, and it wasn't always the robot's fault. In fact, how can the robot crash a PC unless it accidentally rams into it? But that was never the case. So smart cameras are also a great solution. All of the image capture and analysis is done by the camera itself. It's a compact, usually pretty affordable, and it gets its answer, and it can communicate either directly to the robot through I/O or to the PLC. And there's all sorts of different smart camera options out there, 2D and 3D. They can come with built-in ring lights or not. They can come in IP67 industrial enclosures or not. And they're a great solution, but they don't take advantage of the integrated advantages that I mentioned, as far as the cabling and the sole support, and the reliability. So now, whether it's integrated vision or not, you have the choice between a robot-mounted camera and a fixed-mounted camera. In the upper right, I've got a picture of a fixed-mounted camera fixed to some extruded aluminum looking down, but also on the robot tooling, there's a camera mounted on the robot. So one of them, when the robot moves, the camera moves with it. The other one, the camera stays still. So with a robot mounted camera or cameras, you mount the camera on the end of arm tooling, and that gives you so much flexibility. The camera can be positioned wherever you want, wherever the robot can reach. You can adjust its distance from the part, its angle, its height. You can control that. It can act as multiple cameras. The robot can position it over workstation A, and as long as it can reach, it can position it over workstation B and C and D. So that single camera can act as multiple cameras in your work cell. But with that, you have a disadvantage. While the robot is positioning that camera, the robot cannot be doing another operation. It's got one arm, and while that arm is positioning the camera over top of your part, it can't be also loading the machine. It doesn't work that way. If you have one arm, you can only do one thing. So with that camera, you have the flexibility, but it could reduce your cycle time of your work cell. And sometimes it's necessary, and sometimes it's not a big deal. One thing is that with an integrated vision system, the robot doesn't have to stop, take a picture, analyze it, and then move. The robot can go and present the camera to the part, probably slow down a little bit, not stop, find the part. And then while it's figuring out where that part actually is, the robot can be moving towards it. So by the time the robot gets to it, it can adjust its position and move right to it. So the cycle time might not be a huge hit, but there is some. When you have a fixed mounted camera, the cycle time can be 100% buried into your application in many applications. While the robot is loading a fixture or a machine or a tool, a fixed mount camera looking down on your parts can find the next part and already know where the next part is. By the time the robot's done loading it and ready to pick up the new part, the vision system can communicate to the robot where that one is, and it can go pick it up just like it knew all along. So there really isn't a cycle time hit in most applications. But the disadvantage is your fixed field of view. It might take multiple cameras. Here's a robot mounted camera video where the robot's picking up this little toy car, going around and inspecting around the car, looking for different defects, like is it the right wheel? Does it have a license plate? Are the headlights in place? There's specific checks, so specific error proofing that was programmed into it. So it picks it up, the robot mounted camera goes all around the car, looking at the hood. This one, it's missing an interior. Trust me on that one. And then it does its little dance. So a fixed mount camera solution for this application might require a camera on both sides, the front, the back, the top, maybe different angles. Well, the robot provided that. There it found a defect in the door, and it does its little dance. So simple gripper, it goes and picks up the parts without vision because they're fixtured, they're already in the right spot, puts it down on a fixture, so it's always in the right spot, and then uses a robot mounted camera. So there is no robot guidance involved in this video. There is only error proofing, making sure everything's right. That one was missing a headlight. Here the roof is the wrong color, it's blue. So it's going to show the user the blue roof and then do its little dance. So a robot mounted camera provides flexibility. I wanted you to see that. And one last one, I think this is a good car. So, in a matter of a second or two, it takes about 11 shots and looks all around the car to make sure specific errors are not in there. It's not looking to make sure the car is perfect. It's looking to make sure certain things are good. So here's an example of a fixed mount camera. This is a M1 robot. It's a Delta robot, a little bit different than your average 6-axis robot, but still a 6-axis robot. The camera is actually mounted in the base right below. It looks like a helmet of the robot. Let me go back here. Looking straight down at that little tray of pills. This is a pill sorting robot where it's supposed to find all the white pills first, and then the pinkish orangish pills second, and put those in the middle one, and then find the red pills last. So it takes a picture. In this case, it's a color picture. So it's a fixed mounted camera looking down, taking a color picture, finding all the white pills first. And then as fast as the eye can see, gets rid of all the white pills. And then takes a picture looking for the salmon colored pills. all good. And finally, looking for the red pills. And if a pill gets jostled, it doesn't know it until it takes a final cleanup picture and grabs any that are left over. So that's a fixed camera. It can't do anything else. It can't check the level of the pills. It can't do, look at the sides. It just looks straight down, and it's happy all day long. Another topic when we're talking about integrated robot vision is robot guidance versus inspection. And I've mentioned it a couple times here, but going into the details of it, what is robot guidance? Well, it's where the vision system guides the robot to, to often pick or place the part, or however it wants to interact with the, the workpiece. So the robot guidance can be in 2D or 3D, and it can be a robot mounted camera or a fixed mounted camera. And with a robot mounted camera, if you have integrated vision, the robot always knows where it is. And since the vision system is part of the robot, the vision system always knows where the camera is. So no matter where that robot moves in its envelope, the robot knows where the camera is. So it's kind of a great little marriage. With inspection, the vision system is used to inspect the part and then communicate the results to the robot. So it's not necessarily saying where the robot is, it's just saying, or where the part is, it's just saying whether it's a good part or a bad part. Both are great applications, and sometimes you can combine them. If you have an application that requires robot guidance, why not also add a couple simple checks in there for probably won't cost you any more. You've already got the hardware and the software, and maybe it won't even cost you any cycle time. You can add those checks in there to make sure it's the right part or the previous operation happened or not. So you can often get away with doing some error proofing on your guidance applications, more or less for free. And some jobs, the robot's only job is to hold the camera. So here's an application where the robot is holding the camera in this enclosure. There is no tooling. We're not picking up the part. We're not pointing. We're not welding. We're not doing anything with this robot other than holding a camera, a very expensive tripod. So this application, the operator puts the EV battery in front of the robot, signals the robot to find the battery because he didn't put it in the exact same spot, and then goes over and does some checks as the robot goes and make sure everything's okay. Then it'll communicate to the operator, yes, that is a good part, and the operator will take that information, in this case, add a little green sticker to the part and put it in the good section. Then they'll grab the next one that they're inspecting, put it in front of the robot, signal to the robot to start, and it'll start taking pictures, making sure, whatever the quality team has decided is a valuable inspection. Here the screen turns red, the robot's flashing above it, telling the operator, yep, there's a defect right there. So the robot was able to communicate that to the operator, and so the operator was able to put that part with a sticker showing what is bad, put that part in the bad pile or something. Here's an example of robot guidance. This one also involves a conveyor belt, so the robot is picking up the parts on the fly as we go. In this case, it's 3D. It's looking straight down at the parts as they go underneath the conveyor. A sensor gets hit, tells the camera to take a picture as soon as it's underneath, and you get a 3D picture. In this case, the demo is showing off a little bit that we've got zebra patterned parts on a zebra patterned conveyor belt to show that you don't need to have a perfect looking part on a perfect looking background to still find it. And the vision system's driving the robot to the center of the parts. They're all at different heights. They're all at different angles. Some of them are even crooked or tilted. So the 3D vision system is communicating that to the robot, and it's picking up and it's loading the tote. So I mentioned there's a conveyor. Not every robot application has a conveyor, of course, but it was still a cool video that I wanted to show you. Now, is it a 2D or a 3D application that you need to consider? And to be honest, the application usually defines it for you. It's rare that you have to pick. It's usually pretty obvious. With a 2D application, the workpieces are allowed to move in X, Y, and rotation on a flat plane like a conveyor or a work surface or a fixture. So thanks to gravity, parts usually sit flat on something. So most of our manufacturing applications allow that, but not always. If they don't, if you need a 3D offset, which is X, Y, Z, yaw, pitch, and rotation, if you need that 3D offset, you can have a 3D sensor on your vision system and find the parts in 3D. With 3D, maybe the parts are different heights, maybe they're stacked on each other and they're scalloped a little bit, so they start leaning as you get more and more parts, and you need to know that. Maybe the parts are in a rack and the rack allows the parts to move around a little bit in 3 dimensions. Or hanging on a conveyor and it can twist and swing a little bit, then you need 3D. So either 2D or 3D and a fixed mount or a robot mounted camera. Here's an example of 2D with another tracking cell. I don't know why I showed 2 line tracking cells in a row, but it doesn't matter. What this is, there's a camera just to the right of the screen looking down at all these random batteries, and it's looking for batteries. I'm gonna play that one again. It went way too fast. Right there is a vision system looking straight down at all the batteries, communicating to this robot where the batteries are, but also communicating where the batteries are not. So it can group them together based on an algorithm saying, okay, if I start here, I can go here, here, and then here to give me a 4 in a row. So it's using intelligence to figure out how to do that 4. It's not always going 1, 2, 3, 4. If the first battery it finds has space for 1 on the right and 2 on the left, it'll use that information and create the 4 in a row that way. And it does it pretty quickly. So let's group them together so that the second robot can do 4 at a time and simulate loading the machine. So one robot moves quick and small motions. The other one is slower and longer motions. So that's an example of 2D. If the batteries were tilted for some reason, the vision system probably just wouldn't find them and they'd go into the reject pile. It's not trying to drive the robot in 3D. But some applications, the parts are in 3D. Here is a bin of boxes. Maybe at your local post office, your package came in this bin and the robot has to unload them so that it can go onto a conveyor and get its barcode read, perhaps. So it goes in, finds the part, and picks it up and loads a conveyor. Here we can see the overhead camera because we're looking straight up, looking down every time and finding a pickable part. In this case, not only is the vision system finding the part, but it also knows the size of the part because sometimes the 4 grippers won't land on it. If it doesn't, then it'll only turn on 2 of the 4 cups and pick it up that way. Oops, I meant to hit pause. Anyway, I missed it. So if it's small enough, it only energizes 2 of the suction cups and picks up the part that way. So that's a case where 2D would not work because the parts are different angles and different heights. Another thing that integrated robot vision can do, or any vision, is inspecting and error-proofing the parts. But I've dealt with lots of customers that says, can your robot tell me if it's a good part or a bad part? And I say, that depends. What's the definition of a good part? They're like, well, I don't know, it just has to be good. Well, machines aren't very good at it just has to be good. You need to tell them the difference between good and bad. You need to tell them what you're looking at. With inspection, are you looking for surface flaws? Are you looking for dimensional tolerances, burrs in the part, weld quality, bead inspection? Does the bead have any gaps? Is it the right volume? For weld, is it a good weld? Well, with a vision system looking from overhead, sometimes that's tough. Let's say you wanted to look for burrs, and maybe the burr is kind of hidden inside the hole, underneath it. Well, unless it's X-ray vision, no vision system is going to be able to see a burr that's hidden. So there are things that people want to do that are just not practical, Or maybe they require special lighting or special cameras. Maybe they require 50 cameras looking all around, or really small ones, or special lenses. So there is inspection in the machine vision world, and that's all fine and good, but that's usually over the head of a integrated machine vision system. The error proofing, though, on the other hand, is often much easier. It's more like gross inspection. Is it the correct part? Did the previous operation happen? Is it upside down or right side up? Here in this example in the lower left, this is a pokey yoke. Does this part fit into that part? Well, you can see that it does not. But did you actually measure to make sure this distance is the right? Would this fit into this hole? Or did you say it didn't work because the square doesn't fit into the round? What if I had 2 cylinders? Then you'd say, yep, they would fit. Well, that's error proofing. But what if I'm asking you to, well, is the distance between the 2 holes right? Are the holes the right size? Can they actually fit? So that's more like inspection. Instead of saying, pass or fail based on a quick check, you're actually looking at everything. Maybe these holes aren't drilled out yet or drilled deep enough. Well, that would be an inspection you would need to make. So error proofing is this fails because the square does not go into the round. Inspection is it the right size? Are these the right depth? Are these the right tolerances? Lots of different things. Or over here on the right-hand side, inspection, looking at this Class A surface, making sure the contours are all right. Well, in this example, you're not really even looking at the part itself. You're looking at how the light interacts with the part, which is all fine, but it's impossible to say, yep, a simple error proofing can tell me if this is a good part or a bad part. There is way too much going on. You would probably need a specialized inspection station, or oftentimes human operators are still pretty good at these complicated surface law stuff. So machine vision can do quite a lot, but I don't want you going away that machine vision can do everything. And in this case, it takes specialized lighting, but really I don't even think I mentioned that all machine vision, you want to control your lighting. Maybe it's a ring light, maybe it's an overhead light. It doesn't have to always be specialized, but you also don't want to rely on the factory lighting where the old 100-year-old sodium vapor light bulbs are eventually going to burn out, or somebody decides to turn off the light switch. You don't want your production to stop running. You want to control your light, whether you're doing inspection, error proofing, or robot guidance. So my goal today was to kind of get you thinking about integrated robot vision and more so just robot vision in manufacturing altogether. So adding vision to an automated manufacturing process, it can easily add flexibility. There's all sorts of more things you can do once you have an intelligent robot. You can also improve quality. Instead of the robot just blindly picking up the part and jamming into the machine and going and pick up the next part and jamming it in again, you can start to put in some checks to make sure that the parts are the right location, or the right surface, or the machine is ready for the next part. The sensors can often be used to determine if there's a part in the machine or not, but maybe it'd be cheaper and easier to add a camera to make sure there's a part in the machine or not. There's all sorts of, there's no exact one way to do it. Machine vision adds the flexibility. And often you can reduce cost. Thanks to a machine vision system, it is often cheaper than having a complex fixture designed and built and redesigned and rebuilt and stored and figure out a way to do changeover and keep that going. A machine vision system can help you do your automatic changeover, or it can help you have the flexibility that you need. And also it can increase throughput quite a lot of times by finding the part. Maybe you find the closest part or the best part, and you don't have to hunt and peck or go to the wrong part. So with increased intelligence, the throughput can also sometimes go up. Sometimes it is slower to have a vision system, but if you know that going in as part of your cell analysis, then you can handle that and you can figure out a way to make it fit into your work cell. And as far as using integrated vision, the integrated vision will help your automated manufacturing process in a few ways as well. For starters, it's going to reduce your work cell complexity. Simply having the robot and the machine vision system made by the same manufacturer is just one less player in the on the field. So you might have a conveyor company, a tooling company, and a robot company. Well, at least you don't have the fifth one, a vision company. So have the less people you have involved, often the easier it is, and often the cheaper it is, the less markups you're going to have to do. So reducing those numbers of key suppliers is really a win for everybody, especially when it comes time for support. The robot manufacturers, they have 24-hour support. You call them anytime you want and talk to them. Well, if it's integrated vision, then the support is going to come from the robot manufacturer. But maybe the third-party vision system that you purchased, they might be a company of 5 people and you might not get 24-hour support or the ability to have somebody on site by morning. So relying on well-established manufacturing partners like the robot companies, helps out your bottom line quite a bit. And also improved reliability. Robot manufacturers are very keen on having reliable processes, because as soon as that production goes down, the phone call starts, everybody starts losing money. So the reliability is a key factor in people's decisions to purchase or repurchase robot systems. If there is a proven reliability reputation, then that shows and people are very happy. If the vision system is part of the robot, then the reliability also has to be adhered to. So that's why the reliability is important for the robot manufacturer who makes the vision system, because it's also his vision system, his or her. So with those reasons, the integrated vision offers quite a bit of flexibility and advantages. So anybody have any questions? I can open up the questions tab. You can as well, and we can see what types of questions going in. So while those questions come in, I want to thank you, but also thank the NTMA team for putting together this this forum and having FANUC have an opportunity to speak and talk about some of this stuff. I personally am able to have the advantage of working with robots and vision systems every day, but not all of you are. All right, here's the first question here is, with a 2D robot application, what types of field of view can you get with an integrated vision system? Okay, so an integrated vision system using 2D, actually it depends on the lens you choose. So you can have a field of view looking down at your part, and it could be as microscopic if you want. And so a couple millimeters square field of view, that's one extreme. Then your average field of view, a foot or two by a foot or two, or even a large field of view, an entire car body at one time with the right camera lens and the right distance away. So the field of view, the camera lens, and the distance are all related together. Sometimes if the field of view is going to be too large, you might want to break it up into multiple fields of view, what we call a multi-view, where you have a field of view, one camera looking down at one corner of your large object, another camera looking down at another corner of your large object. And based on where those two corners are, you can combine the location to give you one offset, one location of those. Because since it's assumed to be a large rigid body, the relationship of the two doesn't change. So the location can be figured out that way. Or even if you have a 3D object that's large, you can look in 3 dimensions at 3 different corners and find the plane of this this large body. So the field of view is really unlimited, and all depends on your lens. All right, another question here based on lighting. The question is there any lighting suggestions you have for a robot application? And unfortunately, there isn't a single lighting solution, just like there isn't a single robot gripper solution. It all depends on your application, but there are a few kind of general purpose lighting strategies. And one of them would be a ring light, a small light around the camera looking, in the same direction as the camera to illuminate what the camera sees. And that's great because it's easy, it's cheap, it's easy to install, and no worries, right? But the challenge is the ring light illuminates a field of view about the size of the ring light. So that's only good for your smaller field of view. I would not want to use a ring light to illuminate a whole 48 by 40 inch palette, because what you'll end up with is a hot spot in the middle and quickly go to darkness at the edges. So a ring light or any overhead lighting with maybe multiple lights looking down at the project or product. And then there's backlighting if your application allows, or you can light from the side. There's quite a few different lighting techniques that you can do. And whenever people are struggling with lighting, I tell them they can work with a lighting vendor. Throughout the country, there's quite a bit of lighting vendors that specialize in lighting. I specialize in robots and vision, so I know what's going on with the lighting, but there's actually optic engineers out there that can support you, and often they'll support you for free, assuming you're going to buy their product. So you can send them a part and have them analyze what's the best lighting for a camera to see. And quite often, people will send me a part and say, is this a good vision application or not? And I'll put it under a camera, I'll mount the camera to the robot and see what's going on. And I'll use some of my own lighting tricks. And sometimes I'll say, yep, you want to do this with this lighting and you'll get this type of accuracy. Or sometimes, unfortunately, it's my job to say, sorry, this probably isn't a good application. We want everybody to win, and if you were to go down this road, you would probably struggle and be unhappy. So anyway, lighting is a long story, and there's probably some webinars to focus specifically on lighting. All right, another question coming in talking about accuracy. People want to know what kind of accuracy you can get with a vision system. And like the lighting question is, there is no number I can get. It really depends on the application and the part. And in my experience with a robot application, the accuracy is usually going to be, kind of hard to judge, and not the vision system causing any inaccuracies, since it's the robot, the gripper, and the part all have their accuracy tolerance. The vision system accuracy tolerance is usually better than those. So it's when you're adding up all of your error tolerances or your stack ups, the vision system usually isn't a big player. And as a rule of thumb, and some people might cringe, any robot application that you need better than a millimeter, then you're really going to have to start thinking about using some of your higher accuracy tools. If it's, you need to be within a millimeter or two, well, then the robot's going to have no troubles finding it and picking it. The robots themselves are not perfect. They're not designed to be, perfectly accurate. They're designed to be good enough for 99.9% of the applications. So accuracy is always a challenge, and sometimes it just has to be tested to see what you're going to get. All right, let me look here. That seems like I'm good here on questions. I'd like to thank you guys for listening to my presentation and hope you learned something about robotics and vision. I'd like to thank NTMA for hosting this and getting you guys together. I think it's important that all these different manufacturing partners get together and work together so we can have nice quality manufacturing systems. And that's it for questions. Please feel free to contact me at FANUC America. My name is Josh Person, and I look forward to hearing from you guys, down the road. Thank you. Goodbye.